You are welcome to the GMAETS 41's live class. In this particular class, we are going to deal with energy quantization and photoelectric effect in physics. Once again, you are welcome. So we do not have enough time to waste. For as we know, the exam is fast approaching. JAM examination and of course WAEC. Sadly, as it could be, in a society where we find ourselves, was it on Saturday? I don't know. I got a pop-up message from the guys. Yeah, the guys, because I don't understand anymore. A high-profile professional examination as JAM cannot stick to a particular time when they decide to kick off the examination. 25th. And now 24th. I think they did something a kind of similar last set. I don't know. But that is so bad. And sorry to say, it's barbaric. It's uncivilized. Because, I don't know. An individual may be like, oh, it's just 24 hours difference. The truth is that as students, 24 hours means a lot. Yes. As students, 24 hours means a lot. And I just pray and hope that many who are scheduled to start this exam on Thursday, 24th, as they've adjusted, they can do their best. Because I had known that some people would have scheduled their own mind, conditioning that even on Thursday, they are going to do some personal reviews. But all the same, like I said, this is a society we find ourselves where anybody can just wake up and do anything, not really considering what is going to be the effect to the other people. I would have thought that JAM should have considered very well the impact this might have on, even if it is one student. Yes, the impact it may have. I was just reading through the news and, reason they were given is irrelevant and insensitive. Yes, it's irrelevant and insensitive. I just hope that this could get to any of the JAM official and all the professor in charge. This sudden adjustment is insensitive. Speaking, I'm not taking JAM, but as an educator, we understand what it really means when exam timetable is just being adjusted unnecessarily. Yeah, it's unnecessary because no cogent reason was given. And even if a reason is being given, at least any adjustment should bear in mind or should be targeted towards giving students the best. But this one now, no. It's giving students the worst. Yeah. But all the same, I wish you guys all the best. I got your back in the best I can do for you as always. And today we'll be looking at this topic. Once again, you are welcome as we kick off. Like I said, we don't have enough time. Energy quantization, photoelectric effect. Now, when we talk about energy quantization, what is this all about? Now, if you have an atom, okay, if you have an atom, and then we usually see something like this in chemistry as an atom, and then we have electrons. We have electrons distributed, okay, and then let's say we have another electron here. When this atom is excited, how do you excite an atom? By giving it energy. The atom being excited, the electrons will jump from a lower energy level to another higher energy level. When the atom gains energy, we say that electrons in the atom, they will jump. They will exhibit a quantum jump, moving from one lower energy level to another higher energy level. If I call this, let's say, E0, which is the ground state, the lowest energy level that can be attained. Let the energy level be N1, corresponding to read the energy should be E0, right? E0. Energy level 1, N1. Then energy level 2, N2. Let's E1 be the energy of that state. And then energy level 3, N3. Let E3 be the energy value of that state. You likely would have heard in chemistry the concept of quantum numbers. where you have principal quantum number, azimuthal quantum number, magnetic quantum number, something. The principal quantum number are these energy levels. Corresponding to the energy levels, we have these values of energy attached to them. This E0 is the ground state energy level, the lowest possible energy level that is allowed for an electron. Because after that, you have the nucleus. And the electrons are not meant to spiral into the nucleus. They are not meant to fall into the nucleus. They can only go higher. And if they are falling, the least energy state they can fall to is this energy level 1. Now, like I said, when you excite this atom, either by heating it, take note, you excite either by heating the atom or subjecting the atom to high potential difference and low pressure. High potential difference and what? Low pressure. The electrons you have here, they will start jumping from lower energy level to a higher energy level. So let me assume that, okay, this one jumps to this energy level. Let's say that this one jumps to this energy level. It is possible also that maybe this one will jump to this energy level and then again jump further to this energy level. Am I communicating? Now, the movement of this electron from one energy level to another energy level is said to be quantized. Is said to be what? Quantized. And what do we mean by saying that this energy of the electrons is quantized? That it is quantized means it is discrete. It is what? Discrete. And then a student might still wonder, what do we mean by discrete? In statistics, we are told the concept of discrete takes whole numbers. Takes what I said, whole numbers. So the whole idea is that as the electrons jump from one energy level to another energy level, the amount of energy they will absorb before they move is quantized, is discrete, is a whole number. It is what I said, a whole number. So I could say something like 20 kilojoule, 30 kilojoule, 50 kilojoule. You are not expected to get intermediate values. You are not expected to get intermediate values, values within whole numbers. So that is the whole idea, that the energy of the electrons is quantized. Energy is quantized, meaning it is discrete, meaning that they have whole number value, that is, i.e., whole number values. Whole number values. Good. So we have gotten the concept of energy quantization. It simply suggests that the energy of electrons is quantized, is discrete, when electrons move from one energy level to another energy level. Or we can say, when the electron is falling down, because it is possible for the electron to emit energy, to give out photon, right? Through radiation. The electron will lose energy. That losing of the energy, we refer to it as emits. If an electron emits, radiates, give out energy, what is expected? For the electron to lose energy, it means that the electron, instead of jumping to a higher energy level, it will fall down to a lower energy level. So this movement you see, up, 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 you can still get a corresponding down, down, down. You can still get a corresponding what? Down, down, down. Like I said, the least downward fall that the electrons can exhibit is that which will bring them to the ground state. This state E0 is called the what? The ground. The ground state, which is the lowest ground state, which is the lowest energy level allowed. All right, so that is the concept of energy quantization. Good evening, Chibike Moses, you're welcome. Ebere Fikaro, good evening, you're welcome. Emirachi, you're welcome to join the class. All right, so we'll be moving on, having explained the concept of energy quantization. Now, this energy is like a packet. Okay, when electrons, they emit energy by losing, or they gain energy, absorb, and then they jump to higher energy level. This energy, they come like a packet. Okay, remember I said that the quantity of that energy is discrete, whole number values. That energy which is quantized, like I said, it comes as a packet. We refer to it as photon. So a photon is just like a packet of energy. You can also call it quanta. Okay, is a packet of energy. Packet. If I give you a packet of something, they come as whole number. Now you count 1, 2, 3, 4, 5. Is that okay? All right. So when you hear photon or quanta, please take note that it means a packet of what? Energy. So this is what electrons either give out or gain. When they give out, that is emission. They emit it. They lose that energy. They could also absorb, gain. When they absorb, when they gain, they jump to higher energy level. When they emit, when they radiate, when they give out, they will fall down to lower energy level. Now, this will take us to Max Planck's radiation equation, because Max Planck proposed the value of the energy in this case when these electrons, exhibit this quantum jump. Max Planck proposed the energy value. According to Max Planck, all right, that value of energy. Okay, let me indicate as Max Planck's radiation theorem. According to Max Planck's radiation theorem, okay, we have that the value of that energy is equal to HF. That energy, that photon that is absorbed or emitted by electrons is given by HF. Well, generally we could put NHF here. Let me say this is equal to, and then we have NHF. All right, where n equals 1, 2, 3, and it continues. N is an integral value. N is an integer, but the integer starts with 1, 2, 3. So you can say that n is simply a natural number. 1, 2, 3, 4, 5. Remember, we said that the value of that energy cannot be it can't be a value within whole numbers like decimal values and stuff like that. It can't be. It can be. So we don't expect to get something like energy to be equal to 1.5, HF. No, this must be whole number, because the energy of an electron is quantized, is discrete, is a whole number. So you can't have continuous values like this. In statistics, numbers referred to as continuous are either decimal numbers or numbers that fall in range. Let us say 1 to 3 HF. This is not a discrete value. This is a continuous value. For discrete, it is simply a single whole number. A single what? Whole number. So this is what we expect. 1 HF, 2 HF, 3 HF, in that order. Having stated Max Planck's radiation theorem, usually for calculation, our n, we check it for, the ground state, because like I said, the lowest allowable energy is that in the ground state. So if n is equal to 1, we can just say that E is equal to HF for short. You can see this is Max Planck's radiation theorem. I want to take note of that because it can be tested on this equation. We are moving on. We are going to talk about the energy of an electron. At this point, the energy of an electron in a given energy level. So that's the next we're going to look at. Energy of an electron. Energy of an electron. The energy of an electron is given as E equal to -1 all over square of n, where this n, like I said, is the energy level, multiplied by a constant R, multiplied by a constant R, where E is equal to energy, N is equal to energy level, have energy level 1, level 2, level 3, and then R is equal to a constant. As you move on to a higher level, you find out that this constant is also related to one other constant called the Rydberg constant. The Rydberg constant, but don't worry, if your examiner wants you to solve any problem using this formula, this R value will be given to you. We simply call it a constant here as it is, okay? So just get that to heart. So with this equation, if I tell you that you should find the energy change between two energy levels, n equal to 2 and n equal to 5, for example, find the energy change between two energy levels, n equal to 2 and n equal to 5. All you have to do is to apply this formula. You have that this is going to be E equal to, come to this guy, substitute the value of 2 for this energy level, n equal to 2. If you fix 2 here, you square, you have 1 over 4 multiplied by whatever value of R is given to you. That will give you the value of the energy for this energy level. Then you also solve for this energy level also. In that case, it's going to be E5. The first one, you can take it as E2, where n is equal to 2 in that case. Now, the second guy, the second energy level, E5, E will be equal to minus 1 all over 5 squared, giving you 1 over 25 times whatever value of R given to you. So once you have gotten the two values of E, then you find the difference. Find the what? Difference. Just take subtraction. Ifebuche, you are welcome. Welcome to the class. All right, guys, we are done with this concept. You want to screenshot, you can screenshot. So that I'll wipe the board and then we move on to the proper energy change value when an electron jumps from one energy level to another energy level, because there is this one we specifically use which relates to this Max Planck radiation theorem. But you still need all these guys, you need them, okay? We're going to work more on this Max Planck radiation theorem for a case where an electron jumps from one energy level to another energy level. You know, in that case, you should be talking about changing energy, like I explained here. Okay, but remember, this equation specifically is the equation for the energy of an electron occupying any given energy level. Energy of an electron in an energy level. Let me squeeze it here. In an energy level. In an energy level. All right, finish up this, please. You can screenshot like I've always advised. So that we move on, we're going to be pretty fast in our class today. Remember, like I said, there is no time. The little time you have, had been reduced by the gas. All right, so I'm going to wipe this. At this point now, we are going to bring in the speed of light. We're going to bring in the speed of light because here we are dealing with the concept of energy, and the electrons, they gain energy and they move. The speed of this electron as they move is important. And when electrons are moving, they move supposedly at the speed of light. So we're going to introduce the concept of that speed as well as the wavelength. You know, as the electrons jump from one energy level to another energy level, a distance is covered. So we're going to introduce that. Okay, so let me just make use of this side of the board. Let's take this as equation 1 and take this as equation 2. From equation 1, now recall that F is equal to C over lambda. Definitely you would have seen this formula, relationship between frequency, speed of light, and wavelength. We met this formula on the wave, right? Wave and as well as sound wave. Under electromagnetic field, we met this guy. So it implies that if we now consider this guy, we can write E to be equal to HF, and that is still the same as, in place of this F, you can fix C over lambda. All right, and then that's going to be H times, for F, you fix C divided by what? The wavelength. So we want to take note of what we've established here. What we have succeeded to establish is that E is equal to HC divided by lambda also. So equation 3. Depending on the parameters given to you by your examiner, you now know the formula to use between equation 1 and 3. Equation 1 and 3 are the same thing. This C over lambda, the speed of light over wavelength of the electrons as they exhibit this quantum jam. Speed of light over wavelength is equal to frequency, as I rightly wrote there. Take note that for a quantum jump from one energy level to another energy level, if we said, okay, that this E is equal to final energy level minus initial energy level, let me use EF minus EI. I hope someone will not get confused with this concept of F I used, thinking it's frequency. Okay, let me wipe this. Instead of using final F and I, let me use KSA 2 and 1. Okay, where this is higher energy level, lower energy level. And we can still call this change in energy level, change in the value of energy rather. That would mean that equation 3 can still be written as delta E, change in energy, which is equal to E2 minus E1. And that will still be equal to HF. That will be equal to HF, okay? And that will still give us HF, HC rather, divided by what? Lambda. But one can actually still work on this, that this F will be the frequency of the higher energy level, then frequency of the lower energy level could still be applied there, such that one can see the equation in this format for calculation, but that I am very well certain that you will not be bothered about that, bothered in that direction. Change in energy equal to E2 minus E1. This is energy at level 2 and this at level 1. So it's going to be Planck's constant times frequency at level 2 minus Planck's constant times frequency at level 1. Frequency at energy level 2 minus frequency at energy level what? 1. Planck's constant is common, so you can factorize it out. You now have H, open bracket, F2 minus F1. No need of writing H2 minus H1, because that Planck's constant is a constant value, it doesn't change. And one could also apply it to this. That will now be equal to HC over lambda 2 minus HC over lambda 1. Yes, considering the two different energy levels. However, for calculation purpose, we limit it to this, not considering the other guy, because most times when questions are given to you, it's given in such a way that we don't bother for what is happening. In the case of the other energy level for the frequency and of course the wavelength, because we consider it that the frequency of the electron will still remain the same as it moves from this energy level to the other energy level. Okay, it's just a link, one given frequency. From this energy level to another energy level, you have one given frequency. So that is why we always leave the equation in this format. Now, what is our H. H is equal to Planck's constant. Planck's constant. And of course, that Planck's constant is equal to 6.63 times 10 to the negative 34 joule second unit. So this is the value of Planck's constant. If a question is to be given to you on this, that value ought to be given. C is the speed of light, which by now, I believe that as much as all of you should have memorized that. And the value of speed of light is 3 times 10 to the power of 8 meter per second. Then, of course, this is the wavelength. Wavelength. The unit of wavelength is meter, SI unit, because it's distance. Under wave, we learned it to be distance between two successive crests or troughs. Now, do not forget the relationship between frequency and wavelength. As you can see on the board here, frequency and wavelength, they are inversely proportional. So take note of that. They are inversely what? Proportional. Now we are done with this. These are key concepts you want to take note of as you prepare for your examination. Now we want to define certain concepts, certain terms. We're going to define line spectrum. We're going to define continuous spectrum. We're going to define absorption spectrum. 3 spectrums. In that atomic structure I drew with electrons jumping, from one energy level to another energy level. They leave traces of lines. They leave traces of lines as they jump. Are you following? Rays of light. When an electron moves from this energy level to the other energy level, they usually leave traces of what? Lines. So we're going to define 3 major spectrums. We talk about the line spectrum, we talk about the continuous spectrum, and we talk about the absorption spectrum. You need to know the definition of these guys. So what is line spectrum? Line spectrum. Line spectrum. Definition. But before then, I'm going to just draw this. I'll draw this. I want you to watch these lines. So you can see the lines are well arranged, right? They are well arranged. Okay, let us look at continuous spectrum. Continuous spectrum. These guys, they form what we call atomic spectrum, the spectrum, right, of an atom. In this case, we look at the lights that the atom, the light that the electrons create. And these lights, they come as rays, leaving traces of lines. Are you following, right? In a given atom, when the electrons are jumping. Now for continuous spectrum. Now watch this. You see, I know you don't like this second diagram. You don't like what I am doing because that one is not clearly defined. That one is not clearly defined, right? It's not clearly defined. That's continuous spectrum. This line spectrum is also called band spectrum, B-A-N-D. Band spectrum, line spectrum or band spectrum. Then the last, like I said, we're going to talk about absorption. Absorption spectrum. Absorption spectrum. So what is line spectrum? I'm going to be fast in defining it. If you can put it down, fine. But even if you do not follow up completely, remember at the end of this lesson, a copy of this video will be made available and you can always check back. Is that okay? You can always check back. Line spectrum. This is a spectrum that contains lines of unique colors, frequency, and wavelength. lines of unique color, frequency, and what wavelength. When we say that this thing is unique, it also means that line spectrum is a spectrum that contains well-defined lines of characteristic colors, wavelength, and frequency. So the idea is that in line spectrum, the trace of lines that are left by the electrons when they exhibit, when they undergo this quantum jump, the lines are well defined. They have characteristic defined frequency, wavelength. Are you following, right? Those lines, they are well defined, of unique color, frequency, and well defined wavelength. What about continuous spectrum? Continuous spectrum is a spectrum that consists of light of all colors, wavelength, and frequency. It consists of light of all colors, wavelength, and what? Frequency. So the lines that are formed here, it contains all different kind of lines, interwoven, not clearly defined. Are you getting me right? Not clearly defined. So a spectrum of light where the lines, are not clearly defined. A spectrum that consists of lines of all colors and frequency and wavelength is known as continuous spectrum. I conclude my definition with absorption spectrum. Absorption spectrum. What is it? For you to understand this, I'm going to draw this. Let me assume that, don't mind this, right? Let me assume that you have a gas here. A gas. This is a gas contained here. And then, in this gas, you pass a continuous spectrum through it. You pass a continuous spectrum through it. Let me say that, I think this is going to cut off here. So, I'll shift this to this side so that it will cut off from your view. Now, let's say that these are gas molecules. You now decided to pass continuous spectrum through this gas. Continuous spectrum. You pass continuous spectrum through this gas. You are going to obtain dark lines. You are going to obtain what? Dark lines. Let me make this up a bit. You are going to obtain dark lines, well defined. You are going to obtain well defined dark lines. These well defined dark lines correspond, is the same with the line spectrum of this gas. That dark line that you obtain by passing a continuous spectrum through a gas, that dark line which you obtain is what we call the absorption spectrum. I repeat, you have a gas system. Inside you have gas. You decide to pass continuous spectrum. That is lines that contains light of all colors, frequency, and wavelength. You pass it through this gas. Once you do that, you are going to obtain dark lines. You are going to obtain what? Dark lines. These dark lines, they correspond. They are the same with the line spectrum of this gas. So the dark lines obtained, which correspond to the line spectrum of a gas, when continuous spectrum is passed through a gas, that dark line is what we call the absorption spectrum. So these three definitions are very important. You want to take note of them, right? Angel, you're welcome to the class. Forest JS, why are they proportional? I don't understand the question you've just asked. All right, let us move on. Difference between both. Izuchukwu Joshua, your question is not well defined, so I don't really understand. Is there a difference between line spectrum and continuous spectrum? If that is what your question is based on, then it's important for you to know that line spectrum contains well-defined lines. So the lines are clearly separate. They have unique frequency, they have unique wavelength. Right? But for continuous spectrum, as you can see, the lines are not defined. They don't have unique frequency. They don't have unique wavelength. Now, I might not be able to go deep into this, especially because of time factor. However, at least I've been able to carry out an experiment, when I had the opportunity to run a project work for a polymer and textile engineering student. That was in 2017. Yes. On how we can use local material to produce paint thickener, cellulose of cassava. I remember that we sent that sample at the time in Nigeria. Only one university, I think ABU Zaria, had that machine that resolved that cellulose obtained, extracted from cassava stem, and we were able to see the continuous spectrum of that guy. And so, but I cannot talk about it fully now because you don't even really need it right now. So let's move on. I've defined these guys as you expect to know by your examiners, and of course, I've told you the difference between them. Now, take note, you use continuous spectrum to obtain absorption spectrum by doing what? Passing the continuous spectrum through a gas. Then it will produce dark lines. That dark lines is the same as the line spectrum of that gas. Okay? So you want to take note of the relationship. And that is it. Your examiner might just ask you of their definitions. That's what they will ask you about them, nothing else. Dash is a spectrum of light that consists of well-defined lines of characteristic frequency and wavelength. The correct answer will be line spectrum. Right? The spectrum obtained when continuous spectrum is passed through a gas is known as dash. The correct answer is absorption spectrum. Finish up with what is on the board so that I can wipe it. This will now take us to the next and supposedly the last part of energy quantization and photoelectric effect. We are done with the concept of energy quantization. Don't forget these formulas we've brought out. You can use them for calculation. Your examiners can ask you questions on that. All right, so take note. When we are done, as time would permit, we'll look at some questions about them. We have a lot to cover tonight, remember, because of the sudden adjustment of your exam date. So you want to stick around because you know we've got a lot of wonders to learn. Now we are going to deal with photoelectric effect now. In this photoelectric effect, we'll look at the concept of threshold frequency. We'll talk about work function. We'll talk about the stopping potential, the electron-volt concept. We're going to also learn what determines the maximum kinetic energy of photoelectrons. We're also going to learn about what the number of emitted or liberated photoelectrons depend on. What does it depend on? So these are the concepts we want to treat now. I would like to wipe everything from the board. So make sure you finish up. I hope you've screenshotted this stuff. So we go. Photoelectric effect. What is photoelectric effect? Before we kick off, I'd like to mention the concept of solar panel. This is something that most of us have been used to, right? Yeah, because we see it a lot. Photoelectric effect. Photoelectric effect. All right, so first, I'm quickly going to sketch, what the tube looks like. In case you see the diagram, so that you would be able to identify it. Okay, so we've got something like this. This is the cathode, this is the anode, and this is connected to a source of electromotive force. This is your cathode, this is your anode. Cathode is negative, anode is positive. Okay, so when light falls on this, let this be rays of light. Okay, so let's say light. It falls on this metal. This cathode is also a metal. It's a metal. If I want, I can still label it metal cathode. If light falls on this metal, electrons will be emitted. Electrons will be what? Emitted. So these are electrons. The electrons, as they are emitted, remember electrons are negatively charged, so they will move from the cathode to the anode. This positive, negative terminal. And so that's it. Then invariably, current will now flow. Current will now do what? Flow. Remember, current always flow in the opposite direction to electron movement. This tube you are seeing here is an evacuated tube. It's an evacuated tube. There is no air in it. It does not contain air. Right? It is an evacuated tube. Glass tube. So this is the diagram of your photocell. We call it the photocell actually. Photocell. And I don't know if I would be able to. I had wanted to show you a solar panel, but we really don't have that much time. I'd have shown you a solar panel, how this works. But all the same, no problem. I wanted to go get one and show you. But let us say just some time to come, be able to display that. All right. Now, this light that is falling on this metal, causing the metal to emit electrons. For the light to do something to this metal cathode, it means that light has energy. And what is happening here is called photoelectric effect. So let us define that phenomenon, photoelectric effect. Are you ready? I'm going to write the definition here. Photoelectric effect is a phenomenon whereby light falls on the surface, or whereby electrons are emitted from the metal surface when light falls on that surface. A phenomenon whereby electrons are emitted. Electrons are emitted or liberated. You can either use any of the words. When light falls on simply on the surface. On the surface of metal. Phenomenon whereby electrons are emitted from where? From the surface of the metal. When light falls on a metal surface. When light falls on what? A metal surface. Like your solar panel, when light falls on it, what happens? Electrons are being emitted. And when you connect that solar panel to a source of potential difference, what is going to happen? Light will be produced. Maybe you just give me a moment. Give me a moment. I'd like to just show you something quickly, okay? Just give me a moment. So, let's see this. This is a mini solar panel. This is an evacuated glass, right? Seems like network interfered. I think the network is back over there, right? Is the network back? All right. So, did you follow through when I tried to explain the concept of this? Did you capture it? Chibike Moses, please, can you indicate? Or the network disturbed you? Did the network interrupt when I was explaining the working principle of this photocell? Chibike, did the network you when I was explaining this, or you? Okay, let me not say or. Let's answer in one direction. Okay, the network disturbed you. All right, back to what I said. This is your solar panel, right? And it operates based on the principle of this photocell. Light will fall on this panel. Light will fall on it. This is an evacuated glass tube. And you can see inside lines like traces, paths where electrons flow. When light energy falls on these from the sun, are you getting? Because usually for this to work, you keep it under the sun. It receives the light energy. If you remove it from the sun, nothing, it cannot do anything. It can't. So it works based on light energy. So if the light falls on it, electrons will be emitted, will be liberated. Now, you can see from behind a conductor, connected wire. If you connect this conductor like this wire now, you can see that to a source of potential difference. This panel can be used to produce current. You can use it to, like I used to light a little bulb and use it to power a little fan, right? When this is connected, when you connect to a source of potential difference. Now the light energy that fell on this, that light energy has a given energy in it. That energy is given by Max Planck's radiation formula. Energy is equal to HF. So when the light falls on this, that total energy from the light is given as HF. That energy is divided into two. One part of that energy will free the electrons here. As this thing is like this, the electrons are not free. Yes, they are held bound. I hope network is not. Is network still disturbing you? As this thing is, at this point, I think everything is okay. Electrons are held bound to this metal. They are not free to move. That's why it's not powering anything. It's not. But if this were to be kept under the sun, it will receive light energy, which will lose the electron, like a kind of free the electrons, lose it, unbound it from the metal. Does that make sense? And that total energy also has another part of it. Depending on the frequency of that light, it has another part of it that cannot make the electron to start moving. To move from, say, this point to this point. To travel. And as they travel, of course, they leave lines, like we've treated on that line spectrum. So as they are traveling, once you connect these to a source of potential difference of EMF, you can now use this to generate light. Current will start flowing. So that is the working principle of this. And like I've shown you, the energy from the light source is divided into two. So at this point, we are now going to talk about that energy. This will take us to Einstein's photoelectric equation. The equation that we use in resolving what is happening there is called the Einstein's photoelectric equation. Remember, I told you light falls on that metal. Electrons are being unbound, liberated from the metal. Depending on the frequency of that light, the electrons can gain kinetic energy and start moving. So, that total energy is divided into two. Remember that energy is given by Max Planck. And Max Planck radiation formula is E equal to HF. This is the total energy falling on that metal. Now, that energy is divided into two parts. One of the parts is called the work function. One of the parts is called the work function. This work function is an energy. It is the minimum energy that is required to liberate an electron, to lose an electron. Are you following? To emit an electron from a metal surface. But that will not give the electron kinetic energy. It won't. So, this first part, or one part of this total energy falling on the metal, then plus the second part is now the kinetic energy. Is now the kinetic energy. Permit me to use K for it. Yeah, in most sources or textbooks, you see this in as E. But I don't want to confuse this E with this one. I don't want to. Even if I fix E here, please take note that this is kinetic energy. This is what? Kinetic energy. Or maybe let me use this symbol so that at least it will be close to whatever you might see in any other source. But it doesn't matter. I can use any symbol I want. Let me use this symbol like this. Where E, which is equal to HF, is equal to total energy. Total radiation energy. You know, because the light from the sun, in that case, being radiated towards and into the photocell. Then W is equal to work function. Work function. That W, which is equal to work function, is given as HF naught. It's given as HF naught. It depends on the threshold frequency. It depends on the what? Threshold frequency. That work function. And then this is equal to kinetic energy. Kinetic energy. And of course, you know that your kinetic energy is 1/2 mv squared. I hope our network is still moving. All right. 1/2 mv squared. So we can now say that this equation will now become HF equal to W plus this, which means that our HF will be equal to W. W is HF naught, and then plus kinetic energy. These are various forms in which the equation can take. I've lost count of the equations established, but let's call this equation 4, I guess. Let's call it equation 4, I guess. All right. So this equation, you are seeing either this one or this one because they are the same thing. HF here is this your E, total energy. HF naught is your W, work function. And then half mv squared is your kinetic energy. This equation is called Einstein's photoelectric equation. Take note of that. It is now time for us to define certain terms. We are going to define the threshold frequency of this light that is falling on the metal so as to liberate electrons. We are going to define the work function. And then I'm going to tell you what the maximum kinetic energy of the photoelectrons. Photoelectrons are the electrons emitted. Those are electrons liberated. What the maximum kinetic energy of those electrons depends on. Okay? And then, of course, we are going to find out what determines the number of electrons that is going to be liberated, that is going to be emitted in the process. Finish up what is on the board. Finish up what is on the board. Finish up so I can wipe off. We are dealing with Einstein's photoelectric equation. And this is the equation. Breaking it down, I've told you the meaning of these guys. All right. M here is the mass of an electron. In fact, M equals mass of an electron. Mass of an electron. Mass of an electron. And the mass of an electron is about 9.1. Think times 10 to the power of minus 31 or so, right? The mass of an electron. If question is given to you in exam, I think your examiner is meant to give you that value of the mass of an electron. That is if you are given a question on that. Is that okay? All right, I'm going to wipe this part of the board. Now, how do you determine the kinetic energy of the electrons that are being emitted? This will take us to the concept of stopping potential. Stopping potential. You know, as the electrons are being liberated and they move, as the electrons are being liberated and they move, if you want to stop the electron, you have to apply another energy. Electrons are in motion, kinetic energy. I want to stop them. You have to apply a form of energy which is potential in nature. A form of energy which is what? Potential in nature. And that we call stopping potential, V. Stopping potential, V. So what should you know about it? Kinetic energy should be equal to an energy that contains that stopping potential. And then I want to recall this formula, or you want to take note of this formula, please. Kinetic energy is equal to EV, electron-volt. Don't worry, we are still going to define those things I told you. which means that 1 all over 2 mv squared is equal to EV. This EV is known as electron volt. That EV is known as what? Electron volt. Where E is equal to electron, a charge of an electron. In some sources, you might see this E as Q. It means charge. Charge of an electron. Of an electron. Charge of an electron. For you to remember this concept, take your mind back to electrical potential. Electrical potential. We met that under electrostatics. We met it under electrostatics. Electrical potential. Remember, electrical potential is V. And we defined it as the work done in bringing unit positive charge from infinity to a point in the electric field. The work you will do to bring unit positive charge from infinity to a point in the field. So electrical potential V is equal to the work done divided by the charge you are bringing. This formula you are seeing, if you cross multiply, you will get W to be equal to QV. This formula is the same as this electron volt. This E here is the same as this Q. This V here is the potential difference, which in the case of photoelectric effect, we refer to it as the stopping potential. Stopping potential because you have to do work in order to bring the electrons, which are already moving, in order to bring them to rest. Stopping potential. The potential to stop the electrons from moving. This is work done. So we are saying that kinetic energy of the photoelectrons is equal to the work you will do to stop those electrons from moving. And that work you will do is given by what we met under electrostatics, like I said, electrical potential. To work on this, you make W subject to the formula. This Q is the same as E, like I said. So this is not a new formula to you. It's not a new formula. What is the charge of an electron? The charge of an electron is equal to 1.6 times 10 to the power of negative 19 in the unit of Coulomb. The charge of an electron has this value. So you want to take note of this conversion factor, please, because we can convert this into energy. I have been able to prove to you that this formula is not new to you. Yes, I've taught you, you've met it under electrical potential. So since this whole guy is an energy, EV together is an energy. E alone is charge. V is potential, stopping potential. That's the term we use to define it here. It's the same as electrical potential as you met under electrostatics. But here we'll call it stopping potential. E is the charge. Together, they give you an energy. They give you what I said, an energy. The work you will do to stop these electrons that have kinetic energy from moving. So since this whole quantity is an energy value, we want to take note of this, please. 1 EV pronounced as 1 electron volt. 1 electron volt. The energy value is 1.6 times 10 to the power of minus 19 joule. So you want to remember this conversion factor, please. 1 electron volt is equal to 1.6 times 10 to the power of minus 19 joule. Take note that this value and this value are the same thing per se. Yes. However, this is the value of charge alone. Why this is the value of the energy together, EV. Why they are exactly the same? Leave that for now. Why they are exactly the same? Leave that for now. We are moving on. So we use this to convert any electron volt value to energy value or energy units. If I tell you what is the value of 5 electron volts in joule, what you do is simply to multiply that 5 electron volt, 5 EV, by 1.6 times 10 to the power of minus 19 joule, and then you convert it. We are moving on. We are now back to define the following concepts. We are back to define the following concept we have here. We're going to define the threshold frequency first. And I think threshold frequency. Threshold frequency. Threshold frequency, we use F0 for it. Definition. This is defined as the frequency of light which on falling on a surface, metal surface, is sufficient to liberate, to emit electrons without giving them any kinetic energy. I take that definition again. Threshold frequency is defined as the frequency of light which on falling on a surface, on a metal, is sufficient to liberate, to emit electrons without giving it kinetic energy. The frequency of light which falling, I can say that will fall. Let me make the grammar quite straightforward. All right. So if you're reading, you understand what is there. That will fall on a metal in order to liberate electrons. Without giving them kinetic energy. So when that total light falls on that photocell, the metal surface, the frequency of light that will cause electrons to be liberated, to be loosened, to be unbound from the metal. Remember, if there is no light falling on that metal, the electrons will be held strongly to the metal. So it's just like what I taught you under semiconductors, that naturally the electrons, they are stuck to that semiconductor. So only if you increase their energy, they will now be agitated. In this case of photoelectric effect, they will be excited and then, ready to move. So that frequency of light that will make the electrons to be liberated, but without giving them kinetic energy, without making them to move, is what we call the threshold frequency. There is a graph about threshold frequency that you are expected to know as you prepare for your exam. Okay, now this graph, this is maximum kinetic energy, KE. And then we are plotting it against frequency. We are plotting it against what? Frequency. If you plot the maximum kinetic energy of the emitted electrons, please, the emitted electrons are called photoelectrons. They are called what? Photoelectrons. That's the name given to them. Let me identify this point, and then you have this line. That's the graph. That is the graph. This point is your threshold frequency. This point is the threshold frequency. Remember, where these two lines, vertical and horizontal, meet is the origin, 0. Then the frequency will start increasing. So this point where this graph cuts the x-axis is called the threshold frequency, which you have defined here. That is that frequency of light that will cause electrons to be liberated from a metal without giving further kinetic energy. Now I want to take note of this. Below this threshold frequency, less than that threshold frequency, no electron will be liberated. No electron will be liberated. Take note of this. Below the threshold frequency, less than the threshold frequency, there is no photoelectrons given off, liberated, emitted. It means that if the light falling on that photocell, the frequency of that light is less than the threshold frequency, no electron will be liberated. That photocell will not do anything. Just like the solar panel I showed. Imagine that the weather is very dark. There is something I used to observe about that solar panel, right? If I keep it outside, if I keep it outside, and I plug it to a source of potential difference, say maybe a fan, and then when the day is bright, there's going to be light because electrons will be flowing, electron will be emitted, liberated from that panel, and they'll start moving. Are you getting me right? So if I connect that wire, that conductor to maybe like a fan, it will power the fan will work. Now, depending on the intensity of that sun, yeah, let me say sun now, because light, let it not seem as if it's one other thing we are talking about. Sun, depending on how high that sun is, the working or the time during which the panel will work will be sustained. But let me tell you what happened. If maybe the weather goes, let's say, how do I put it, dark, no sun, no radiation, no real radiation, the fan will not be working. The fan will not be working. Why? Because the energy from the sun that is now falling on the metal does not have that frequency that will cause the electrons to be liberated. It does not. So what we are saying is that for photoelectrons, for electrons to be liberated from the photocell, please, the light falling on that metal, the frequency of that light should be either equal to the threshold frequency or above the threshold frequency. If it is less, nothing is going to happen. So it means in this direction, like this, from here to this direction, electrons are liberated, liberated from the threshold frequency and above. But below the threshold frequency, from here to this point, not liberated, not liberated. This is an exam question. You want to take note of that. I hope what I drew on the board did not cut off. Let me adjust it a bit, please. Let me adjust the camera a bit. Just a bit. All right. One time, Mami, you are incredible at your doing. Keep up the good work. Thank you very much for the commendation. One time, Mami. Thank you very much. I appreciate it. And thank you for connecting to the class. Without you friends being there, there's nobody I would teach. Okay, so we have the electron. You now understand this concept, like I said. It's an exam question if you are tested in this area. Okay? Listen to this. Which of the following is true? Which of the following is true about photoelectric effect? If examiner wants to specify that it's photoelectric effect problem. A. Electrons are liberated when the frequency of light falling on the metal is less than threshold frequency. B. Electrons are liberated if the light falling on the metal has a frequency equal to the threshold frequency or above. Then C and D, other useless options. So the correct answer is option B. For photoelectrons to be emitted, the light falling must be at least the threshold frequency value. The light falling on that metal, the frequency should be equal to the threshold frequency or above. Below it, nothing is going to happen. All right, we are done with threshold frequency. Let's now talk about, before I move on to work function, take note now that the kinetic energy, note. In fact, I'm going to use mathematical approach to write this note. Kinetic energy, the maximum kinetic energy is directly proportional to frequency. Take note of this. I don't want to speak any big grammar about that. What does this mean? It simply means that kinetic energy depends on frequency. Kinetic energy depends on what? Frequency. That's the meaning of this. The kinetic energy of the emitted electrons will increase if the frequency of the light falling on that metal increases. The higher the frequency of the light, the greater the kinetic energy. So you want to take note of this fact. But kinetic energy does not depend on intensity, does not depend on intensity of the light. It does not depend on the intensity of the light. K is directly proportional to frequency F of light, which means that the maximum kinetic energy of the emitted electrons, they depend on the frequency of the light, but they do not depend on the intensity of that light. They do not depend on the intensity of the light. Finish up this, let's wipe the board, and then we talk about work function. Work function. I'll try to take a snapshot of this as well too. It will be used as notes for some persons. All right, so that's it. Finish up. I hope you screenshotted it. So I'm going to wipe this now. Work function is the next thing we are going to define. Work function is the next thing we are going to define. Work function. Work function. W. We define work function as the minimum energy that is required to liberate electrons from the surface of a metal. The minimum energy required to liberate electrons from the surface of a metal. That's what work function is. And mathematically, you want to take note of this. The work function W is equal to HF naught. I've actually told you about this. Work function depends on threshold frequency. It depends on what? Threshold frequency. All right. If work function depends on threshold frequency, the formula is going to be written like this. So if you know the threshold frequency of any light falling on a given metal, to get the work function of that metal, multiply that threshold frequency by the Planck's constant, 6.63 times 10 to the power of minus 34 joules second. All right. Note, I want to tell you what determines the number of electrons emitted. What determines it? Note, the number or amount of emitted or liberated of emitted photoelectrons depends on the intensity of the light energy. So you want to differentiate between this and this. Kinetic energy, maximum kinetic energy, depends on frequency of light. It does not depend on the intensity. That is for kinetic energy. However, the number or amount of emitted photoelectrons, the number of electrons emitted, depends on the intensity now. It depends on what? On the intensity. That is the amount of light ray falling on that metal. When maybe you keep a solar panel, for example, outside under the sun, and then the sun starts dimming, the frequency of light falling on that solar panel will reduce, but possibly the amount of which is the intensity of the light, the amount of light ray falling per area of the surface might still be the same. I'm going to tell you what we mean by that. Look at this surface. When you talk about intensity of light falling on it, it means the amount of light ray, light energy falling on this given area. So intensity of light on any surface is based on the area of that surface. If maybe the panel is as small as, let's say that the panel is of this size. It's of this size. You know that this size is less than the size, the area of this device, this phone is less than the area of this. The intensity on this guy will be different from the intensity here. So the greater the intensity, which depends on the surface area, the more the number of electrons that will be emitted. So if I have a solar panel of this size, and I have a solar panel of this size, this one that has greater area will absorb more light in terms of the intensity of light due to the area. So more electron will be emitted here than this one. More electrons will be emitted here than this one. That is what we are saying. That the intensity of light determines the amount of electrons emitted. But when I'm talking about the kinetic energy of the electrons, okay, the electrons are now to move. They are to move. The kinetic energy has nothing to do with the intensity. The area of the surface has nothing to do with it. It's only the frequency that determines the maximum kinetic energy. Because whether the panel, the photocell is small or large, whether it is large or small, if you have enough light energy of high frequency, the electrons will move irrespective of the surface. So when you expose the solar panel to burning flame, will it cause the electron of the solar panel to be emitted? Well, that I have not tried. However, I would say no to it. Why I would say no to it is because in physics, we have what is called thermionic emission. When you're dealing with all this modern physics, we have thermionic emission. I mentioned that when I talked about semiconductor in our previous class, telling you that PN junction diode can be used as a thermionic diode. In the case of exposing it to maybe something like heat, because fire in that case, it is heat that guy is bringing. It is heat that it is bringing. There are devices that are being constructed or designed with respect to such kind of thing. It's not solar panel. Solar panel is designed with respect to light energy, not thermal energy. Do you get that? So for this, it's not going to work. If you expose the solar panel to fire, I don't see it working. All right, guys, we are done with this. I've defined the work function, and I think that is that. That's the concept of what you should know under energy quantization, right? So you finish up what is on the board so that we can now look at 1-2 questions on this. We've covered what you are meant to know under the concept of energy quantization and photoelectric effect. Although the concept of X-ray comes under here, but you can read up that because X-ray follows this principle as well too. If I have something like tungsten metal, there is this metal, okay, from the element called tungsten. If light falls on it, right? If light falls on it, that guy will emit X-rays. it will emit X-rays. X-ray is still all these electrons of a thing, and which we use to get the image of the inner body. Now, I want you to learn about these, please, types of X-ray with respect to soft and hard X-ray. Learn about them and their characteristics. Is that okay? You can just Google them. If you have your textbook, you can pick it and read up. Okay, type of X-ray. Application of photoelectric effect. Application of photoelectric effect, or simply photocell, because the cell from which we study this photoelectric effect is called photocell. Solar panel is one good application. Are you following, right? Solar panel is a very good application of this guy, so you want to take note of that. Burglar alarm doors, right? Burglar alarm is also another application of the photocell. Television camera is also another application of photocell. Automatic doors is another application of photocell. So take note of these applications I have mentioned, okay? So do you have water there? Yes, I do have water. Let me take a drink. You know, this is the one I take. I don't have money to buy bottled water. So thank you for drawing my attention to this circle. I appreciate it. I really need this. But something with me is once I handle this marker, I don't know, every other thing just I just forget that. I need this. Let me take this water. People should not laugh. I consume water a lot. I don't know me and Carmel, who consumes water more. I'm going to finish all of them. You see, right? Water is good. Thank you once again, Circle, for drawing my attention to it. Remain for you, producers. You don't finish, you. You don't finish. Don't worry, I'll teleport your own to you. Okay, guys, we are done with this concept of energy quantization and photoelectric effect. Think within the time left before 2 hours. Let's see, how long we've spent. This is 1 hour 31 minutes. So roughly 1 hour 32 minutes. We shall use the remaining time to answer some past questions from this guy. Okay, shall use the remaining time to answer some questions. There is, high degree of breeze here from the surface of a metal. I just hope the breeze will not blow off the network, because whenever I experience this, the network will start misbehaving. If it does, well, I'll just release a pre-recorded video where I answer some questions on this. I hope the network is not messing up over there. Okay, let's see. Well, we've got our very first question. Trying to please, this breeze, calm down. The network I use, it doesn't joke with breeze at all. Once breeze comes up, it will just do boom. So just pity us. Okay, so we've got this first question. Which of the following statements is true of photoelectric effect? Which of the following statement is true of photoelectric effect? I want to be sure that the network isn't disturbing. It's happening. Okay, so option A, it cannot occur in liquid. Remember, the question is, which of the following statements is true of photoelectric effect? Option A, it cannot occur in liquids. Option B, the energy of the emitted electron is independent of the work function. C, the energy of the emitted electron depends on the wavelength of the incident light. The energy of the emitted electron depends on the wavelength of the incident light. D, the greater the intensity of the incident light, the greater the energy of the emitted electron. The greater the intensity of the incident light, the greater the energy of the emitted electron. So what is the correct answer? Remember, the question asked, which of the following statements is true of photoelectric effect? Option C is the correct answer, which said, the energy of the emitted electron depends on the wavelength of the incident light. Good enough, we have the graph here. The energy of the emitted electron depends on the wavelength. Now you have frequency here, no argument. But remember that frequency is also related to what? Wavelength, inversely. Inversely. So instead of frequency, we can have wavelength instead. And this graph shows that the energy is directly proportional to the frequency. Remember, frequency and wavelength are inversely proportional, which means the energy will be inversely proportional to the wavelength. The smaller the wavelength, that's the distance, right? Covered. The distance between maybe the source of the light energy and the photocell. The smaller the distance, the greater the kinetic energy of the photoelectrons. Because it's going to be an inverse relationship, since kinetic energy and frequency are directly proportional. So the correct answer once again is option C, that says that the energy of the emitted electrons depends on the wavelength of the incident light. You could also say depend on frequency. That we have discussed. Let me wipe this. So that is question number 1. Answered. Option C is the correct statement. Q1 is C. Question number 2. The photocell works on the principle of the A, voltaic cell, B, emission of electrons by incident radiation, C, emission of protons by incident electrons, D, photographic plates. The correct option is option B, emission of electrons by incident radiation. That is the principle upon which the photocell works. You know, light rays will fall on the photocell, radiation, incident radiation. Incident means falling. So radiation falling on, a metal, and then electrons will be emitted. That's the principle of operation of the photocell. I'll tell you the question again. The photocell works on the principle of the correct answer, emission of electrons by incident radiation. Question number 2, C is the correct option. Is it C I said, or B? Sorry, B. Emission of electrons by the incident radiation. I hope network is not disturbing at your end. Okay, still okay here. Still okay here. Let's take the next question. Question number 3. The maximum kinetic energy of emitted electrons in a photocell can be increased. The maximum kinetic energy of emitted electrons in a photocell can be increased by A, increasing the wavelength of the incident light. I think so. B, increasing the intensity rather of the incident light. Increasing the intensity of the incident light, that one is completely off. The kinetic energy has nothing to do with the intensity of the incident light. I explained that clearly to you. Option C, increasing the brightness of the incident light. No. Option D, decreasing the wavelength of the incident light. And option D is what I am going for. You have to decrease the wavelength. Q3. Option D. The first is C, this is D. Listen to the question again. The maximum kinetic energy of emitted electrons in a photocell can be increased. How can you increase the kinetic energy? The maximum kinetic energy. And I'm telling you that according to option D, we are told decreasing the wavelength of the incident light. And that is what I feel is the correct answer. Why? This is the reason. From that graph, we know that the maximum kinetic energy depends directly. Yes, it's directly proportional to the frequency. You saw how the graph went. It's directly proportional to what? The frequency. Are you following, right? The greater the frequency, the greater would be the kinetic energy of the electrons. And we know that frequency is inversely proportional to wavelength. So you can see the relationship now. Kinetic energy and wavelength are inversely proportional. So if you want to increase the maximum kinetic energy, you have to decrease the wavelength. That is why the correct option is option D, not option A. Option A said increasing the wavelength of the incident light. If you increase the wavelength, the maximum kinetic energy will reduce. And that makes sense. It makes good sense, this relationship. If the source of light is very far off and the photocell is taken very far off, it will take a longer distance. Are you following, right? For the light to reach that photocell. Therefore, the kinetic energy will be affected. But if they are close, yeah, the shorter the wavelength, the light reaching it, the frequency will be high. And once that happens, the maximum kinetic energy will increase. We are moving on. Listen to this question. Question number 4. If the light with photon energy of a packet of light. Remember I told you photon, quanta, they are the same thing. Packet of energy of light. If the light with photon energy, 2 eV, is incident suitably on the surface of a metal with work function 3 eV. I repeat that again. If the light with photon energy 2 eV is incident suitably on the surface of a metal with work function 3 eV, then option A, no electron will be emitted. No electron will be emitted, option A. B, the few electrons emitted will have a maximum kinetic energy of 1 eV. Option C, the few electrons emitted will have a maximum kinetic energy of 3 eV. Option D, many electrons will be emitted. For me, I feel that no electron will even be emitted at all. Take a look at the question, understand the question. If the light with photon energy, so energy of the light E equal to HF, has been given to be 2 eV. So this is the total amount of energy falling on that metal surface. Yeah, the question say incident suitably. If you like, let it be suit and completely suiting. This is the total energy you are applying. and you are telling me that the work function of that guy, the work function is 3 eV. So the work function of the metal is 3 eV, which means the minimum, the smallest amount of energy you require to even liberate the electron is this. This is the smallest amount of energy you need. And now you are supplying a total of 2 electron volts. With this condition, no electron will be emitted. No electron will be emitted. No electron will be emitted. And that goes with option A, said intensity, no electron will be emitted. Option A. And I've told you the reason. Because the total amount of energy is less than the work function. Bello Eniola, yep, I got it right. Eniola, don't mind the way I'm pronouncing. Okay, option A, that's correct. Please give me a moment. Is that okay? I'll be back. Just look through this. All right, thank you for the little timeout. You're welcome. As we move on to our next question, let's see what we've got here. Question number 5. Okay, Q5. So we have this question and it reads, a light of energy 5 eV, a light of energy 5 eV falls on a metal and the electrons with a maximum kinetic energy of 2 eV and the electrons with a maximum kinetic energy of 2 eV are ejected. The work function of the metal is, I take that again. A light of energy 5 eV falls on a metal and the electrons with a maximum kinetic energy of 2 eV are ejected. Ejected means to be liberated, to be emitted. The work function of the metal is, so it's very simple. If you look at the question, we're given that the light energy falling, which is E equal to HF, is equal to 5 electron volts. From the question, we are given the maximum kinetic energy. If I use this, which is the same as Ke, which is the same as half mv squared. From the question, it was given, the kinetic energy is given to be 2 eV. and you are simply asked to find the work function. Now you know that the work function is equal to hf naught. That is Planck's constant times threshold frequency. However, do you think you can use this formula to obtain that work function using that particular formula hf naught? No. The information given to you here, there is no threshold frequency. So you can't use work function equal to hf naught to solve. Therefore, you want to rely on the formula that connects work function to kinetic energy and total energy falling on the metal. And of course, that's going to give us that E is equal to, which is hf, is equal to W plus kinetic energy. We are looking for this. Work function, make it subject to the formula, is going to be the total energy minus the kinetic energy. Fixing up your values, you have this to be total energy is 5 minus 2 the kinetic energy, and of course we've gotten 3 electron volts. Listen to the options. Option A, 0.4 electron volts. B, 2.5 electron volts. C, 3.0 electron volts. D, 7.0 electron volts. And you agree with me that the correct answer is option C. We are moving. It's raining over here now. I'm really just hoping that this does not cut off the network. So far the network is behaving well. Please let it give us time to round off. All right, now this will take us to the next question. The energy associated with the photon of a radio transmission at the energy associated with the photon of a radio transmission at 3 times 10 to the power of 5 hertz at 3 times 10 to the power of 5 hertz is, then in bracket we have Planck's constant H equal to 6.63 times 10 to the power of minus 34. I'm going to read the question again. The energy associated with the photon of a radio transmission at 3 times 10 to the power of 5 hertz is, then we have Planck's constant like I said. Question number 6. Now from the question, we've been given the frequency at which the radio station or what have you is transmitting. Just like if you're hearing news from radio station or watching, your news from television station. They transmit at certain frequencies. So the frequency, according to the question, was given to be 3 times 10 to the power of 5 hertz. This is a simple question. The Planck's constant, 6.63 times 10 to the power of minus 34 joules second. We are asked to find the energy of the photon associated with that. So what do we do? Remember your Max Planck's, your Planck's radiation formula, that E is equal to HF, which means that our E is going to be equal to 6.63. We are multiplying it by 10 to the power of minus 34, then times 3 times 10 to the power of 5. So our E is equal to, I had just, released work on standard forms. I released that video in the GMAETS 41's basic class channel. I told you, make sure you follow up GMAETS 41 on both channels, because there are a lot of basic level knowledge that you need at this level also to be able to handle some calculation stuff. And you see this thing about standard forms, right? Scientific notation. Don't joke with it. You need it a lot in the aspect of your physics. Yeah. All those times 10 raised by this and that. See, one of the ways to help you handle that quickly is your knowledge of standard form. So in this case, we're going to multiply 3 by 6.63. And whether you're using that calculator system, at least it will be faster for you to press that 6.63 times 3. Instead of going to press 6.63 times 10 to the power of minus 34, you are dragging your mouse and other things. In fact, that calculator in the system does not even have power. I don't think it has. I don't think so. But in either case, whether it has or not, the fastest thing to do here is multiplying 6.63 by 3. And if you multiply 6.63 by 3, let's see what you're going to get. 3 times 3 is going to give us 9. 3 times 6 is 18. Write 8, carry 1. 3 times 6, 18, plus the 1, 19. So this is 19 points. Remember, before I multiply this 3 by 6, you have a point. Times 10 to the power of, add these powers. Minus 34 plus 5. Minus 34 plus 5 should give us what? Minus 29. Minus what? 29. Minus 34 plus 5 is same as 5 minus 39. Or you can 5 minus 34. Or you can simply just do 34 minus 5. 34 minus 5 should give you 29. Then because the bigger number is carrying minus, you attach that minus there. Now this is still equal to 1.989 times 10 to the power of minus 20 to the power of minus 30. Minus 30 joules. And I move this point once. I've treated all of those things, so it's not something I want to waste my time on. Move the point once to the left. Oh, if you move to the left, you add to the power. You don't subtract, you add. So this is going to be minus 28. Minus 28. So this is going to be the energy associated. Options provided. The options provided. Options provided. Where is the question? Okay. Option A, 2.00 times 10 to the power of minus 29 joule. 2.00 times 10 to the power of minus 29 joule. Option B, 2.00 times 10 to the power of minus 28 joule. Option C, 1.30 times 10 to the power of minus 29 joule. Option D, 1.30 times 10 to the power of minus 28 joule. Now, if you look at this, their answer is in one decimal place or even whole number. So we have two in one decimal, the other in as a whole number. Now, this guy you can approximate to 2.0, you know that. So this is 2.00 times 10 to the power of minus 28 joule. And that goes with option B. So the correct option here is what? B. Where will I write it? Let me fix it to option B. And then that's the calculation. Hello, sir. This is very helpful for my test on photoelectric effect next week. Your videos help me understand all the theories of Newton, Dr. Stroh, GMAETS, and Planck. All right. Thank you very much. I'm glad that GMAETS 41 is of help to you. And I'm committed to the process to helping you friends as much as I can. Bello and Niola, you wrote 1.9 times 10 to the power of minus 30. Good enough. You still highlighted that you made a mistake, and I hope you've corrected that mistake. That is with respect to point movement. Go to our second channel for basic level of learning, right? The name of that channel is GMAETS 41 basic class. That GMAETS and 41, spell it together. Don't give any space. And don't put this hypersan down. GMAETS 41 together. Then you space. Basic. You space. Class. You get a video lesson where I treated the concept of standard form. I released that video, I think that was yesterday, specifically with you guys in mind. We are moving on, please, to the next question. I'm wiping this. So if I am releasing these videos, even if they appear in our basic class, and it's something you need, of course, you want to assess them. You know, when you are making research to learn certain things, it does not matter the level you learn it from. But at least for your coming up with 1.9 times 10 to the power of minus 30, it shows a high level of understanding to what we are doing here. Let's take the next question. Let's take the next question here. If electrons are accelerated from rest through a potential difference of 10 kilovolts, if electrons are accelerated from rest through a potential difference of 10 kilovolts, what is the wavelength of the associated electron? What is the wavelength of the associated electron? In brackets, we are given the mass of an electron. But I don't know. I'm scared of the mass of the electron given here. I'll read it out. But I'm sorry, I may be forced to use what I know as the correct value of the mass of an electron. It could be typographical error here, I don't know. In bracket, we have m equal to 9.1 times 10 to the power of minus 13 kilogram. That power, the last time I know about mass of an electron, is wrong. It's actually minus 31, so maybe just a little mistake. We're going to use the minus 31, okay? I mentioned it when I was teaching, explaining the concept of photoelectric effect. So the mass of the electron was given 9.1 times 10 to the power of minus 31. Yeah, we have 13 here, but forget about that. Kilogram. Then E, which is charge of an electron. 1.6 times 10 to the power of minus 19 coulomb. And then Planck's constant, H, equal to 6.6 times 10 to the power of minus 34 joules second. 6.6 times 10 to the power of minus 34 joules second. It's not compulsory for you to have these three. So whatever they give you there, you use, okay, for the Planck's constant. This is question number 7. At least we'll take up to 10 as usual. Then we'll know we've covered some things as per questions that you might need. Alright, so where are we? If electrons are accelerated from rest through a potential difference of 10 kilovolts, so we are giving V, potential difference, stopping potential, whatever I want to call it, 10 kilovolts, solve in SI units. So this is going to be 10 times 10 to the power of 3 volts. 10 times 10 to the power of 3 volts. I hope the network is cooperating. That's good. And then we've got other values given to us. Mass of an electron, 9.1 times 10 to the power of minus 31 kilogram. We're given the charge on an electron, 1.6 times 10 to the power of minus 19 coulomb. Then, of course, Planck's constant, 6.6 times 10 to the power of minus 34 joules second. And we are asked, if the electrons are accelerated from rest through a potential difference of 10 kilovolts, what is the wavelength of the associated electron? Wavelength, we don't know. Wavelength, we don't know. So let us deal with this question and see how we solve it. What we are looking for is the wavelength. Now recall. We have Einstein's photoelectric formula or equation, right? But you know that we also know that half mv squared is equal to EV. Half mv squared is equal to what? EV. And this guy is equal to, could have written it under so it doesn't cut off. I hope this space is going to take it. All right, I was going to say is equal to HF this is your kinetic energy. Can add it to the work function. So minus work function. Minus what? The work function. Remember this relationship. Remember this relationship. Now what we are looking for is the wavelength. What we are looking for is the what? Wavelength. This is velocity. And of course it's the velocity of the electron. This is velocity of the what? Electron. But what we are looking for is the wavelength. Wavelength is in this guy. Wavelength is in this guy. The frequency of this was not given to us. The frequency of this electron was not given from the question. Let me take a look. Yeah, frequency was not given, and we are asked to find the wavelength. Now remember that E is equal to hc divided by what? Lambda. So all we have to do is to check for the quantity, the value given to us. What would solve it? Now this energy, which is equal to this guy, because this is HF. HF minus the work function is equal to the kinetic energy. Because remember from Einstein's photoelectric equation, look at it. This E, which is HF, minus the work function is equal to what? E. So what we are going to do is that this E as the energy, since we're not given the frequency, we could solve it by equating it to these quantities given to us. We can equate it to this quantity given to us. And then we know the electron-volt value. The mass of this guy was given to us. The speed of the electron. The speed of the electron. Now, the E here, which is HF, like I said, the frequency was not given to us, and I'm still looking at this particular question because I expect that the frequency ought to be given. I expect the frequency ought to be given, so we could obtain the value of this energy. But if the frequency is given, then the wavelength, there will be no need. We could just use the wavelength directly. Anyway, let's substitute here and see what we're going to get. We're going to equate this is equal to this. They give us this guy. Make it equal to the kinetic energy. And the kinetic energy is equal to this whole guy. All right. So this is what we are going to do. Like I said, the challenge is we don't know the frequency, but we can factorize the frequency from here. I know W to be equal to this times. Let's assume that this frequency is given as the threshold frequency. I can rewrite the formula to be half mv squared equal to EV. Then we get the velocity. The velocity of the guy was not provided for us. If I get the velocity, I can now use this to calculate. So this is going to be EV, and then fixing up the values, 1/2 times the mass. Mass of the electron is 9 times 10 to the power of minus 31. That's going to be equal to times the velocity. We don't know the velocity, equal to EV. Now the E is 1.6 times 10 to the power of minus 19. We are multiplying by 10 times 10 to the power of 3 volts. Now we are going to calculate the speed of the electron. Right? We're going to calculate the speed of the electron. Once I calculate the speed of the electron, can now use that likely to calculate the value of frequency, and of course we could get the wavelength. So with this, velocity alone is going to be 2 times this whole thing divided by this, and then you find the square root. I'm sorry that I'm not going to show the working. We're going to work it straight on. 2 times 1.6 times 10 to the power of minus 19 times 10. This is 10 to the power of 4 already. So let me write it here. 10 to the power of 4 volts. 10 to the power of 4. You know, applying the multiplication law of indices. Then this is going to be divided by the coefficient of this velocity. So we've got this. Now we're going to obtain that our V is equal to, evaluate this term. I think I'm going to reach out for calculator. I'll reach out for calculator. But in pressing this with calculator, I'll just press 2 times 1.6. Then I'll divide it by 9. I'll use indices law to work out these powers. So let me say the 2 times 1.6 divided by 9. So this will be square root 2 times 1.6 divided by 9, 0.3555, then multiplied by minus 19 plus 4 will give us minus 15. If minus 31 goes up, it will become plus. So minus 15 plus 31. That's going to give us 10 to the power of 16. We shall find the square root of this whole term. Square root of 0.3555 times 10 to the power of times 10 now to the power of 16. 0.3555 times 10 to the power of 16. Going to wipe something here. And now, square roots 0.355 then times 10 to the power of 16. So this gave 5.9 times 10 to the power of, I want to move the point, 1, 2, 3, 4, 5, 6, and 7 times 10 to the power of 7 meter per second. So now I've gotten this, right? This velocity. What I want to do now is to equate the velocity term to this particular guy bearing this hf, and then replace that f with the speed of light. But I could have actually used this EV directly to still obtain the same thing, rather than disturbing myself obtaining the speed or the velocity of the electron. But all the same, it doesn't matter. What I did here is still significant, at least to help you know how to calculate velocity if you are asked that. So from here, I know that this is hf minus this f. Now what I want to do is rewrite this in the form that EV is equal to hf minus hf naught, where I'm going to approximate this to be the same frequency. Where the same frequency, this is going to be a challenge. It's going to be a challenge. I'm looking at this question and it's like something seems to be wrong there. Okay, we could just equate this to the kinetic energy and then see what we are going to get. This is equal to hc all over lambda. Taking this to be the kinetic energy of the electron, which of course is what was given to us there. So if I'm using that, fixing up the values given, 1.6 times 10 to the power of minus 19 multiplied by the potential difference 10 to the power of 4. That will now be equal to Planck's constant, 6.6 times 10 to the power of minus 34 multiplied by 3 times 10 to the power of, but the speed of light was not given, even if it's a constant. Even if it's a constant. I think I will go the other way around to see what I can obtain there. I know the velocity now. Since I know the velocity, could I just use frequency was not given. Frequency was not given. Frequency was not given. So that frequency that is missing is giving a problem to this question. I hope I dictated this. So it could be, if electrons are accelerated from rest, okay, from rest through a potential difference of this. I think I'm the one that made a mistake. It was accelerated from rest through a potential difference of 10 kilovolts. What is the wavelength of the associated? It was accelerated from rest, so I should have gone straight. I should have gone straight, please, even without applying all these concepts. EV is equal to HF. Or since I've calculated my V here, that's this velocity, I could still use this equal to HF. This guy was accelerated from rest. I'm sorry I didn't take note of that concept while I was solving. But like I said, there is no issues. What I've done here is still significant because it could be given certain questions where you are asked to calculate the velocity of the electron. But for this question, I shouldn't have done this since the acceleration is from rest, please. I could have simply used E is equal to HF, and that EV is equal to HF, and this is equal to HC divided by lambda. See, we have the value already. Our electron volt is 1.6 times 10 to the power of minus 19 times 10 to the power of 4, and that's going to be equal to Planck's constant 6.6 times 10 to the power of 34 multiplied by 3 times 10 to the power of 8. This is minus 34. And then divided by lambda. I'm now looking for lambda. So this is going to be cross multiplied, where lambda will now be equal to 6.6 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by this term, 1.6 times 10 to the power of minus 19 times 10 to the power of 4. So this is what I was meant to do. I didn't take into account the significance of the fact that a guy was accelerated from rest. So let us just evaluate this and see. 6.6 then times 10 to the power of minus 34. We'll handle the powers together. Let's finish up this. 6.6 times 3 then divided by 1.6 divided by 1.6. That's 12.375 times 10 to the power of, can now work out this whole power, right? Can now work it out. This is minus 34 plus 8. Minus 34 plus 8 is the same as 8 minus 34. And then minus 19 will go up to become positive 19. So plus 19. And then this 4 will go up to become minus 4. Minus 4. So all is going to be minus 11. Minus 11. We could still write this as 1.2 in proper standard form. 1.2342375. If you want to approximate, you can approximate. Times 10 to the power of minus 12 meters. So that is what I am meant to do there. That's what I am meant to do. Sorry, please. Sorry. You know, I omitted one significant statement from the question, and that cost me something. Let's look at the powers once again, and see this is minus 34, and then plus 8. If this minus 19 moves, it becomes plus 19, and then minus 4. So minus 11. There are 12 points, this, then minus 11. Move this point to put this in proper standard form, then you now have minus 12. So this is what it's meant to be. Like I said, as much as I'm sorry over this because I misapplied, yes, the question. We are told the thing was accelerated from rest. It was accelerated from rest. That's what we're told. And that goes with option A here, 1.22 times 10 to the power of minus 12. 1.22 times 10 to the power of minus 12. Then I have option B, 3.87 times 10 to the power of minus 10 meter. Option C is 2.27 times 10 to the power of 11 meter. Option D is 2.27 times 10 to the power of 14 meters. So we have the correct option to be option A as given. Option A. So please, we really didn't need to go calculate this velocity. The guy was accelerated from rest. Under that condition, when you are told that an electron is accelerated from rest, simply make the kinetic energy directly equal to HF. Or you make EV directly equal to HF. In that case, the work function is taken to be 0. The work function is taken to be what? 0. So that was the error I made. However, I am just a human. Good enough, I went back to reading the question so as to understand that clearly. And I've told you the significance. It was accelerated from rest. So this is what you're meant to do. Is that okay? Please, for this guy, permit me to do this. This is not what you're meant to do for this question. However, you need this in case you are given a kind of question where you are asked to calculate the velocity of the emitted electron. There are sometimes you are given the value of the potential difference, charge of an electron, mass of an electron, and you are asked to calculate the velocity of the electron. This is what you are meant to do. All right. VDM Fans TV, very clear now. All right. I am glad that this is clear. Okay, at this point. Sorry for the mix-up. All right. So let's see if we can take one more question. Let's see. Okay, I have this particular question. Let's see how it goes. This one has taken everything. Question number 8. Remember, we are trying to target 10 questions at least. And I'm looking towards some questions that seem to be a bit tougher, right? That does not mean that you're going to meet tough questions in the exam. Yeah, you're going to meet tough questions. You meet others that are quite simple also. So I have this particular question. Cesium, you know, there is this element called cesium, has a work function of 3 times 10 to the power of minus 19 joule. Cesium has a work function of 3 times 10 to the power of minus 19 joule. The maximum electron of liberated, the maximum energy of liberated electrons when it is illuminated by light of frequency, 6.7 times 10 to the power of 47 hertz. 6.7 times 10 to the power of 47 hertz is, then we have in brackets the Planck's constant as usual. Let me read the question once again. Cesium has a work function of 3 times 10 to the power of minus 19 joule. The maximum energy of liberated electrons when it is illuminated by light of frequency 6.7 times 10 to the power of 47 hertz is, we have the Planck's constant there, question number 8. So what are the parameters, the data given to us? The work function was provided, which is equal to 3 times 10 to the power of minus 19 joule. In fact, when we are done with this question, I would like you to do something just on your own. When you are done solving it, maybe much later, you can come back to this particular live class, right? And then drop your comment as to what is the answer. Or, as I said now, you can still work it out. For this question, what is the threshold frequency of the light? What is the threshold frequency of the light? We're not asked to find it. But you notice they gave us a particular frequency here, but that is not the threshold frequency. So I'd like you to find the threshold frequency, and of course, you know the formula. That one that is linked to work function, since they gave us work function here. So you can solve it, just get a threshold frequency. Okay? All right, where are we? Cesium has a work function of this. Now, what is the maximum kinetic energy or the maximum energy of liberated electrons when it is illuminated by light of frequency? So we're giving frequency to be equal to 6.7 times 10 to the power of 47 hertz. Of course, Planck's constant was given, as usual, it's something we know. I'm tired of writing it. I'm not even supposed to be writing all this. It's just because I want you at least to follow up, since I'm not copying the question on the board. So Planck's constant was given as usual. We are now asked the maximum energy of liberated electrons. So what we are looking for here is the kinetic energy. Permit me to use this symbol. Kinetic energy. That's what we are looking for. So you recall that the total energy HF is equal to work function plus the kinetic energy. You remember this, right? So that the kinetic energy will now be HF minus the work function, as simple as that. We can now substitute the maximum energy of the liberated electron. The electrons have been liberated, so they move. The maximum energy will now be 6.6 times 10 to the power of minus 34, which is Planck's constant given the question, but I refuse to declare it here, times the frequency, 6.7 times 10 to the power of 47. Now we are going to subtract the work function from this guy. Minus the work function is 3 times 10 to the power of minus 19 joule. And so the kinetic energy is now going to be 6.6 multiplied by 6.7. That's the best thing to do. If you are not good with your standard form yet, scientific form, please make sure go subscribe to GMAETS 41 basic class. The spelling of that GMAETS is together GMAETS 41. Then you now space basic, you space class. You need to know very well about how to handle standard form before you sit for this exam. It's going to help you to be fast in certain calculation. So 6.6 times 6.7 now gave us 44.22 times 10. I can now use indices law to work out this. This is 10 to the power this, 10 to the power this, add their powers. Minus 34 plus 47 is the same as 47 minus 34, which is going to give you 13. It's going to give you what? 13. Minus 34 plus 47 is the same as 47 minus 34. And you're going to get 13, like I said. And you are subtracting 3 times 10 to the power of minus 19. In fact, today, I uploaded the video lesson on standard form, how to add and subtract numbers in standard form, in scientific notation. Alright? Now you have it here in physics. So when I dropped that lesson, I had a reason, because of you people. That is actually what people from basic 6, 7, 8, they do. That's primary 5, 6, JSS1 and JSS2. Okay, so you go learn it. Now for us to subtract this, their powers must be the same. The powers of these guys must be the same before you can subtract. You're working without calculator, as the case might be. So what do? I'm going to move this point. 1, 2. You see, this is minus 19. This is minus 19. And this is positive 13. It's not funny. This is terrible. Very, very terrible. Let me look at the work function value given. That power, if it is negative or positive. It's negative. It's negative. It's negative. Now, the options given here, all of them are negative 19, negative 19. So one would try to convert this minus 13 to minus 19. But this is absurd. This is absurd. From what I am seeing, it's not going to work. I really don't have that time to move this point. Because to get minus 19 from 13, you know what to do? It means you are moving this point up to like, if you move to the right, keep moving to the right. What will you do to 13 to get minus 19? 13 minus 13 will give you 0. Then minus 19 is going to be minus 22. Let's say you are moving this point 22 times. Because 13 minus 22 is that going to give us 19? 13 minus what will give us minus 19? Let's solve this simple equation. This will cross. So you have 13 plus 19. Yeah, 32. Not 22. It means I'm going to move this point 32 times so that this power will become minus 19. And imagine I move this thing 32 times for it to become 19. Power minus 19. This will not make any sense. So I don't know. I am worried about what this is going to be. The powers given, something is wrong with the powers. That's what I feel. Now listen to the options provided, because at this point I would use calculator to press that. Let's see if we get that value. But if that is the case, man, now an examiner shouldn't do this. Examiner shouldn't do this. Let's see. HF is equal to W plus this kinetic energy, and then kinetic energy equal to HF minus W. We're not sorry for kinetic energy. All right. So I'm going to press this straight on. Let's see what the calculator will give. But like I said, let me dictate the options. Option A is 1.42 times 10 to the power of minus 19. Option B is 3.00 times 10 to the power of minus 19. Option C, 4.42 times 10 to the power of minus 19. And then option D, 7.42 times 10 to the power of minus 19. All of them in joule. All of them in joule. And there is no way this can give any of the value. 44.22 times 10 to the power of 13. You know, you're not allowed to use this calculator, this particular one, in your exam. And the one that they will provide for you cannot work out this once. So minus 3 times, or open bracket, minus 3 times 10 to the power of negative 19. Negative 19. 44.22 times 10 to the power of 13. Then minus 3. I have to open bracket here. So I think we'll use rule of broad mass to work it out. 3 times 10 to the power of minus 19. So this gave 4.422. 4.422, let's say 2 times 10 to the power of 14 joule. This is what it's given to me, which is expected. Because if I move this thing 32 times, that 32 times, we make this to become power minus 19. And then whatever I'm going to get here, which is actually going to be 4422 0, 0, 0, 0, 0. I think that 1 and 2. Remove 2 from 32, you get 30. So there will be extra 30 zeros. 4422, 30 zeros minus this 3. Imagine you have 4422 with 30 zeros behind, and you are subtracting these 3. These 3 are subtracting, becoming significant. So the answer will still approximate to this thing, to 4422 times 10 to the power of 13, which if you move the point once to the left, you add 1 to the power. So I think there's something wrong with that question. Something is wrong. But based on the question given, this is the answer. This is the answer. There are no two ways about it. But you can't be given any such thing, like I said, being that the power's here. No. Nobody can give any such thing in exam. I'm even beginning to think, are you sure this is not 17? Are you sure it's not 17? If this is 17, and then let me see, I'm just kind of thinking, if it is 17, I have minus 34 plus 17. This is minus 17. It gave minus 17. So if you move this point, to get minus 19, 1 and 2. 1 and 2 to get minus 19, and then you have 4, 2 minus 3, still 4.4 times 10 to the power of something. There's something wrong with the values provided, okay? But please, my interest is not about what they have here. My interest is the question really given and how you solve it, which is what I have done for you there on the board. Now I have this question, although we didn't cover it here, but let me answer it, because it uses one Einstein's equation. Einstein's equation, I think I gave that equation, I think on that one topic like that, I gave that equation, but I have a video lesson on that actually in chemistry Einstein's energy equation of relativity? Are you following? E equal to mc squared. E equal to mc squared. Since we mentioned Einstein here, can actually still bring it in, but we meet that much under radioactivity. And mind you, in this channel, I have a work on radioactivity. Move on to life. Under our life section of this channel, check through the video that covers radioactivity. It's actually from chemistry, and you will learn more about that. So this is the question. Question number 9. The amount of energy released when 0.5 kilogram of uranium burned completely. The amount of energy released when 0.5 kilogram of uranium burned completely is, we're given the speed of light in brackets, C equal to 3 times 10 to the power of 8 meter per second. So we have M equal to 0.5 kilogram kg, and then C equal to 3 times 10 to the power of 8 meter per second. We are asked to calculate the amount of energy released. So using Einstein's energy equation, the formula is E equal to mc squared. If you want to, you can introduce delta E. Changing the energy is equal to this. And of course, that's going to be equal to the mass, 0.5 times 3 times 10 to the power of 8. We are going to square it. Working out this is 0.5 times. This, you can use the knowledge of indices to solve it. 3 squared will give you 9. 10 raised to power 8 squared. This square will multiply this 8 to give you 16. 0.5 times 9 is half of 9. Half of 9 is 4.5. Then times 10 to the power of 16 joule. This is the energy that will be released on burning that uranium completely. That's 0.5 kilogram of uranium. Option A, 4.5 times 10 to the power of 16 joule. Option B, 1.5 times 10 to the power of 16 joule. Option C, 1.5 times 10 to the power of 8 joule. Option D, 4.5 times 10 to the power of 8 joule. And agree with me that option A is correct. That takes us to our last question. Question 10. We've tried. We've spent beyond the time. Advantage is 2 hours 36 minutes. All right, we are still within range as we round off. So let us see this particular question. Let's see this particular question. Turn over to this. And this is the question. Okay, I would read one, read the other one, then we solve. But the first I'm going to read is left for you to solve it. Or maybe I will give it at the end after I solve this one. Let me solve this one, then I'll give you that as an assignment. A light of 6.22 eV. A light of 6.22 eV is incident on cadmium surface. Is incident on cadmium surface. Cadmium is also another element. So a light of 6.22 electron-volt is incident on a cadmium surface. If a stopping potential of 2.1 eV, if a stopping potential of 2.1 eV is required to reduce the photocurrent to zero, calculate the work function of the cadmium in electron volt. Calculate the work function of the cadmium in electron volts. So from the question given to us, the light of 6.22 eV is incident on cadmium, which means that our E, which is equal to HF, is given to be 6.22 eV, the total energy falling on cadmium. If a stopping voltage, rather, not potential, a stopping voltage, that's what's given, 2.1 eV. stopping voltage of 2.1 eV. So we have this to be 2.1 eV, the voltage, stopping voltage. (2.1 eV) is required to reduce the photocurrent to zero. Calculate the energy of the cadmium in electron volts. Calculate the work function rather, not the energy. So the work function we don't know. The work function we don't know. Now, this question is tricky. Very tricky. Are you following, right? Because here they gave us the stopping voltage to be 2.1 eV. We are given the stopping voltage as 2.1 eV. That stopping voltage, V here being 2.1, and we're given the total energy falling on this. Remember that this is equal to the kinetic energy, because we have that half mv squared is equal to ev. And they have given you the stopping voltage, stopping potential. They have given it to us. So you now have the work function to be calculated. So you want to remember that according to Einstein's energy equation, E is equal to, you can say HF, is equal to W plus kinetic energy. Now that kinetic energy now I'll be using EV. I'll be using what? EV in that case. So we are now looking for the work function. So if you substitute the values you have there, if you substitute the values that you have there, 6.22. Because to solve for this work function, you have to collect EV to meet the total energy that is supplied to that metal. Is that okay? Now, the charge of the electron, we know it to be 1.6 times 10 to the power of minus what? 19. So if we work out this, this is going to give us that the work function is equal to E minus EV. Now what is our work function? Work function is 6.22. Now take note that what was given to us here is the voltage. Is the voltage, the stopping voltage. That's what the question said. So this is just what was given to us, this EV. But you notice that this guy was given in EV, this was given in EV. How many EV is this? 2.1 EV. This is 1 EV, but in the question, the stopping potential is given as 2.1 EV. So if you fix up the values, we're going to get that W is equal to 6 points. We have to convert this and then reconvert. This is electron volt. Take note of that. This energy, 6.22 times, don't forget, this guy is EV. E alone is 1.6 times 10 to the power of minus 19. I'm solving this thing in joule, and then I'll now reconvert to EV, because in the option we are told to leave our answer in EV. So this is going to be minus electron volts. Here we have 2 electron volts, 2 EV in this case. 1 EV is going to give us 1 times 1.6 times 10 to the power of minus 9 minus 19, then multiply by this. If I convert this to joule, we are going to get 2.1 then times 1.6 times 10 to the power of minus 19. That's the value of this. So that your work function will now be equal to, I have a reason why I'm doing this, because the examiner could have asked you to calculate this in joule as well too. So what I'm trying to do is to use one stone to kill two birds for you, because this is the last question. If I work on this, you notice that 1.6 is common to both of them. 1 eV is equal to 1.6 times 10 to the power of minus 19 joule. I told you that. So this thing given to us, 2.1 eV. You multiply it by 1.6 times 10 to the power of minus 19 to get the electron volt value. Remember, we have this formula. This guy is representing the kinetic energy. And this is 1 eV. But in the question, we are given 2 eV as what you need to apply to stop that thing. So I decided to convert them to joule first. Multiplying each of them by 1.6 times 10 to the power of minus 19 is to convert them to joule units. So at least you know how to solve that. Now at this point, we're going to multiply 6.22. I could have just subtracted 6.22 minus 2.1. I had wanted to do it for you earlier, but I just decided not to proceed in that way. But if you're an examiner, that is what you are meant to do. Just subtract 6.22 minus 2.1. Straight on. You solve, because in the question we are asked to get our answer in electron volts. I think that's what it said. In electron volts. Get in EV. So if I solve this term that you have there, I am going to get 6.22 times 1.6. And then minus, open brackets, 2.1 times 1.6. And this gives 6.25. 6.25. It's now be times 10 to the power of minus 19. You know, this 10 raised power minus 19, 10 raised power minus 19 is common to both of them. So you factorize the 10 raised power minus 19, multiply this, multiply this. You could also factorize that 1.6 times 10 to the power of minus 19 if you want. Solve that, and then this is in joule. But we are asked to get the value in electron volts, in EV. So you can now convert this by dividing this guy by 1.6 times 10 to the power of minus 19. To convert from joule to EV, you use this relationship. 1 EV is equal to this. Therefore, how many EV will now give you this? Look at it. How many EV will now give you 6.25 times 10 to the power of minus 19? So all you have to do is cross multiply. This joule will cancel. If you cross multiply, EV will survive. Then divide both sides by 1.6. Therefore, our work function is now going to be equal to 6.25 times 10 to the power of minus 19 divided by 1.6. I think 1.6, because that's the value of charge. Alright, so 1.6 times 10 to the power of minus 19, please. Then this 10 to the power of minus 19, they will cancel. This thing is the joule value of what I'm trying to get. Concluding, 6.25 divided by 1.4, 1.6 rather, 1.6 gives 3.9. Gives 3.9. EV. So that is what the value of the electron volt required to bring that guy to a stop. All right. So this is the last question I want you to work on as your assignment. I'll copy the question on the board. A material of work function. A material of work function 5 eV has a threshold frequency. A threshold frequency of dash. Then in brackets, we have 1 EV equal to 1.6 times 10 to the power of minus 19 joule. And then H equal to 6.6 times 10 to the power of minus 34 joule second. Now I would read out the options. Option A, 1.21 times 10 to the power of 14 hertz. 1.21 times 10 to the power of 14 hertz. Option B, 1.36 times 10 to the power of 15 hertz. 1.36 times 10 to the power of 15 hertz. Option C, 1.21 times 10 to the power of 15 hertz. 1.21 times 10 to the power of 15 hertz. Option D, 1.24. 1.24 times 10 to the power of 15 hertz. So those are the options provided for this guy. So solve it, you are looking for the work function. And if you solve it, you can drop the answer in the comment section, okay? You can drop it in the comment section. So this is how far we go with the class today, and I hope you've learned something from the class. It's all right. I'll be meeting you guys tomorrow by God's grace. And as you prepare for your exam, remember you can always do your best at any point in time. Keep doing your best. See you tomorrow. We'll be looking at possibly chemistry. But I intend to run, okay, on Wednesday I'll run a final review where we'll pick questions randomly. So tomorrow we're going to look at chemistry by God's grace. You take care of yourself and good night. Remember to share the video lesson link to your friends so that they can also learn from it.